right, so now I'm going to talk about Newton's method on vector spaces. Okay, and to sort of try to briefly remind you, it's like how Newton's method is derived. Um, so, and let's just try to do this in the scalar case, it's like to begin with. So let f be a map from R to itself, okay, and x star be a root, which is to say that f at x star equals to 0, and then the Newton method is an iterative method. For root finding. With the following update. Okay, so it generates a sequence of iterates. So xk plus 1 is equal to xk minus f of xk divided by f prime of xk. Okay, where f prime denotes the derivative of f. Okay. All right. So a few observations. And I guess I should also write this as, let's call that g of xk. So the first one is that root of f, right, is a fixed point of this function g, okay, which is obtained from f. Okay, what that means, of course, is that if you happen to be at a fixed point, it's like of the function f, it's like then of course this term here vanishes, and you just have xk plus 1 is equal to xk. So a root of f is, by construction, it's like a fixed point of this function g. Okay, and then this thing, so Newton's method is a fixed point iteration. And because it's a fixed point iteration, there are sort of certain convergence results which are associated with this. In particular, it's if you recall the last time we talked about this, if the sort of the derivative, it's like of this function g vanishes at the fixed point, right? Then this fixed point iteration converges superlinearly to it's like to the fixed point, and if it well, I mean, it's like I should also say that there are some sort of smoothness assumptions. It's like, right? So yeah, so if g is c1, it's like, and d of g at the fixed point is 0, it's like then you have a superlinear rate of convergence. It's like what this iterates to the fixed point. And if in addition it's like g actually was c2, then you actually have a quadratic rate of convergence. So the third thing is that as a consequence of the fact that it's a fixed point iteration in particular, if g is c1 and dg at x star equals 0, then we have superlinear convergence. and if G is actually C2, if furthermore, right? If furthermore G is in C2 and also has this property that dg of x star equals to 0, then we have quadratic convergence. Okay. So the remark again is that because of this relationship between roots, it's like at the function f, it's like at fixed points of the function g. It's like you can, and the fact that Newton's method is basically a fixed point iteration applied to this function g, then you can sort of apply. It's like this theorem we discussed. It's like about the convergence rates of fixed point iterations, and all that involves is knowing something about the differentiability. It's like of this function g, as well as whether or not it's it's like its derivative vanishes at a fixed point. Okay. All right. So before we sort of apply, it's like this result, it's like to say something about the rate of convergence of the Newton method. Let me sort of circle back and then try to at least motivate why it is that you have this expression. Okay. All right. So the main reason for this is the following. Okay. So say you have a function f of x, right, and you're looking for the zero of this. Okay, so this is the 0. All right, so you're looking for this point here. Right, then what is the Newton method actually doing? Okay, so what the Newton method is doing is that, say this is where you start off, right, some point which is not the 0. Then what it's trying to do is to construct a tangent line to the function f at that point. And then look for where this tangent line intersects with the x-axis. Okay, so let's say the following. Intuitively, right, the Newton method for root finding is obtained by replacing f of x, right, with its first order Taylor approximation at the iterate. Xk. Okay, so and this follows from the following, that f of x, right, is approximately equal to f at xk plus f prime at xk multiplied into x minus xk, right, plus something which is big O of x minus xk squared. Right, actually, that's an equality, right, by the Taylor theorem. Okay, so that's sort of the Taylor remainder. Okay. Okay, so if you assume that x minus xk is small, which is to say that okay, okay, so actually let me write it this way. I want to write it as the following. F at x star is this. Okay, and of course f at x star, which is the root, is 0. Okay, So if we assume that the difference between the root and the iterate xk is small, then what you can do is that you can ignore the quadratic Taylor remainder term. And what you're left off with is that 0 is equal to f at x star, which is approximately now f at xk plus f prime xk times x star minus xk. Okay, and then you can solve for x star minus, actually you can solve for x star. Okay, so this tells you that okay, so this is minus f of xk is approximately f prime of xk x star minus xk, right? So I can divide by f prime of xk, so this is minus f of xk divided by f prime of xk, right, equals to x star minus xk. I move the xk over, I get xk minus this, and of course this is approximately, right? So, and that's of course, it's like at least the left-hand side of this is exactly the expression for the Taylor update, I'm sorry, the Newton update. So that's saying that xk plus 1, right, should be equal to xk minus f of xk, f prime of xk. So what the Newton method is basically doing is the following, right? So if you happen to be at the point xk, it takes this first order Taylor approximation to the function at that point, and then it finds the root of that linear function, which you can of course always do, and then that is my new guess, or the new iterate. It's like for what the root of the original function is. Okay, so that's basically how the Taylor term, sort of the Newton method, is derived, is by sort of a fairly general process which you oftentimes see in numerical methods, which is to take the problem of finding, say, the root of the function f and approximate the problem. So in particular, you can approximate f by its first order Taylor expansion, and then solving it's like the associated problem, sort of the approximation sort of exactly, right? So, so you replace this function by a linear function, you can find the root of that function exactly, and then the exact solution of the approximate problem, hopefully, is a reasonable approximation of the exact solution of the original problem. Okay, so that's basically what is happening here, and of course, there is some mismatch. It's like, but then you sort of iterate. It's like, and hopefully achieve convergence. Okay, so that's basically the idea, if you will. It's like behind how one goes about deriving the Newton method. And again, this whole idea of taking functions, approximating them, and then solving the associated problem. It's like for that approximate function exactly. That's the basis of a lot of numerical methods. For example, if you do numerical quadrature, Newton-Cotes methods are precisely obtained by taking data. It's like for the function a bunch of points, it's doing an interpolating polynomial and exactly integrating that interpolating polynomial, and then using that answer as an approximation. It's like of the integral of the original function, right? So this kind of process of taking a problem, approximating it, and then solving the approximate problem exactly, and then using that as a approximation of the exact solution of the original problem. That's something which shows up again and again in numerical analysis. Okay, so let me just again remind you of what we have now. You have xk plus 1 is the fixed point iteration of the function g, right, where g is g of x, right, is equal to x minus f of x divided by f prime of x. Okay, so if you want to prove something about rate of convergence of this fixed point iteration, then you need to say something about it's like the properties of this function g. In particular, you want to see whether or not it's differentiable and whether its derivative vanishes. It's like at the fixed point. Okay, so so let x star be a fixed point of g, and if you recall, it's like it being a fixed point of g is also related to it being a root. It's like the original function f. Okay, so for a generic sort of fixed point, right, f of x star is equal to 0, and okay, so no, actually, so for generic fixed point where f of x star equals to 0 and f prime at x star is not equal to 0. Sorry. Okay, so if you know something in psych about root finding, you know that more or less it's like having the function vanish and the first derivative vanishes means that you have sort of a multiplicity in the root, and that's sort of non-generic. Okay, so we're going to assume that you don't have multiplicity in the root. Okay, then you can compute the derivative of this fixed point function at the fixed point x star. Okay, so then you can check that g prime at x star is equal to 1 minus f prime. So I'm first going to compute the derivative. It's like without essentially using the fact that I'm at x star. Okay. Okay. All right, and so this term f prime to f prime, it's like vanishes, right? Sorry, not vanishes, but it's like it limits to 1, so it cancels out this 1 here, and then this term here, it's like is 0 because f at x star is 0. So the point is that the derivative at g at the fixed point actually vanishes. So that gives you superlinear convergence, right? So at least sort of superlinear convergence. And then you can check that G is actually C2, so we have quadratic convergence. Okay, so far it's like we've just done this in the case where f is a scalar valued function. So the next natural question to ask is, well, what happens if f is vector valued? Okay, so what happens if f now is a map from Rn to Rn? Okay, and in essence, it's like what happens, what you have to do is that you have to generalize the notion of the Taylor expansion, right? So, so we have to generalize the Taylor expansion. And again, so f at x star, right, which you know is 0, is equal to f at some iterate xk plus the derivative. Okay, so actually it's going to be the directional derivative in a little bit, so I'll explain what I mean. Xk plus 1 minus xk equals to 0. No, that's already equal to 0, right? okay, where df of x at a point in the direction z denotes the directional derivative. Okay, which is that df of x in the direction z is defined to be the limit as t goes to 0 of 1 over t of f at x plus tz minus f of x. Okay. And then, all right, so again, so this is sort of where I alluded to before, that you have to, so if f is a vector function, vector field, right, you're evaluating at two different points and you have to take the difference. This is sort of where it's like you have to introduce the notion of an affine connection in order to make sense of what it means to take the difference of vectors based at two different points, if you're going to generalize this notion of a directional derivative to a manifold setting, at least for directional derivatives of things which are not just scalar valued functions. Okay. So yes. All right. So all this is, of course, in the setting of f being what you get for root finding. So let me now try to specialize it, the case where it's relevant to optimization. And as we've talked about before, what that involves is having that f be the gradient, it's like of some scalar value cost function, little f, for example. Okay. All right. So let's try to write that down more precisely. Okay. So to apply this to optimization of a scalar valued function, cost function f, right, which again in this vector space setting is just a map from Rn to R, right? We let big F be just the gradient of little f. Okay. Then this method the Newton method reads as follows, right? So the Newton method is just basically obtained by saying 0 is equal to this thing, all right? So f now is the gradient of little f, so this is the gradient of f of xk, right? So let me just write down below, it's like this original expression. Okay, so we have f of xk plus df of xk in the direction xk plus 1 minus xk. This is equal to 0. All right. Okay, so again, f is now, big F is now the gradient of little f, right? So I'm just going to, every time I say big F, I replace it with the gradient of f. That's what I'm doing here. All right. So this expression below is what you would have obtained just for the root finding problem, and this is what you get if you're looking at a special case where you're using it for optimization. Okay. All right, so to generalize this to manifolds, right, we need sort of a Riemannian metric. Right, to make sense of the notion of a gradient, right? So we discussed this before in the context of first order methods and line search methods. And to make sense of the directional derivative, we need to be able to take the difference of vectors based at two different points, which more or less means that you have to be able to identify vectors at two different points, okay, in some sense. Okay, or if another way to think about it is that you have to transport a vector based at one point to another point. So to make sense of the directional derivative, right, we need the notion of an affine connection. And all right, so so that's going to be the next thing which we discuss. Okay, so so let me just stop here for now.